All right, so in the previous video, we talked about how to find electric potential due to some collection of point charges, due to like a single point charge or collection of point charges. But here we're going to talk about how to find electric potential due to continuous charge distributions. Like if you have a long rod, or if you have a sphere or a surface uh, with charges distributed. So that means again very similar to the previous electric field, finding electric field due to this type of continuous charge distribution. We can also find the potential due to this type of continuous charge distribution. Again, let's take this, let's say over here is our object where the charges are distributed, and we can consider that this is not just single, like let's say object, but collection of objects, a collection of charges. That means you can have, very large n number of particles, charged particles distributed. Then what we do, we take just one sample, let's say element from this object, and what we say here is at some point p, then the small element will then give us a potential, which is then given as like dv. So dv is only the potential due to this small element, and it's equals to k then dq because the small element has only a charge dq, where I can take q the total to be the q to be the total charge. That means q thing like this is equals to dq1 plus dq2 plus dot right, dqn. That means we can break it down into like many tiny elements, and then what we do here is you first choose one and get the expression for that, right? So get the expression for that, and then we can then generalize it. That means, like, let's say we can then, all right, so then take a derivative, or sorry, integral of both sides. The left side then basically your delta v, and then the right side here is k dq over r, and then will be, let's say, then considering the contribution from all the those tiny elements from the entire object. That means again very similar, right? Like we did for the electric field. To find the total potential in this case, you need to integrate and to include the contribution from all those elements. The difference here is this is a much simpler integration, simply because this is a scalar quantity. Potential is still a scalar quantity. That means we don't have to look at it in terms of sines, cosines, x components, y components. It's just r here is just a distance from our element to that point. There is no, let's say, components are involved, to find potential. It's just a number, and then what we have to do is just, you can see, right, again, maybe rearrange and replace dq if the dq for each element might be different in a way that each element, if it has a different distance or something like that from our point, point of interest, then we might have to replace dq with, let's say either lambda dl, or replace dq with sigma dA, depending what type of, let's say, distribution we have, or replace dq with then, rho, right, volume density times dv. That will then depend on type of problem that we have. Okay, but in any case, as I said, right, this is technically delta v, but we use that v equals 0 when, let's say the other point of interest, right, is infinity. That means we again saying that when we are finding the potential, this is the potential with relative to some other point. That means, some other point, to make it simpler for us, is then infinity, and then we know that potential over there is 0. That means, for example, if this is my, let's say this is my distribution, here's then point p. In a way, what I'm saying is that I'm gonna, let's say, take a small element dq. So then this is, position 2, for example, where position 1 is infinitely far away. Okay, that means in a way I know that potential over there is 0, so all I have to do is just calculate potential here, and that's my delta v. That means when I then bring, let's say, a charge from infinity to that point p2, then I can in a way say that I can also calculate change in potential and change in potential energy. So r1 here is infinitely, let's say, far away. All right. So um, remembering that we have this equation where delta V equals delta U over Q naught for the test particle. Remember, delta V here is defined as potential energy per unit test charge. So if the charge distribution has sufficient symmetry, we can first evaluate the field using Gauss's law and then substitute the value obtained into this equation. That means using the Gauss's law will help us solve the right side of the equation in a little bit of simpler manner, because remember, this is still let's say a charge distribution, and this equation where delta V equals negative of the integral of E dot ds. From here, this E we can find from the flux, which is, closed integrals E dot dA. That means if I use this equation to find the electric field and then use that electric field here in this equation, and those are two different equations, right? Here in this equation, then I can use that to find delta V. That means sometimes this requires, multiple steps. That means to find my delta V, I need to first, see what this equation, gives me. But sometimes this equation requires me to know the electric field. Then electric field I can find using Gauss's law, because Gauss's law gives us electric field expression in much simpler manner than, let's say, Coulomb's law, right, for different, continuous distributions, right? So, when we're talking about Gauss's law was how to find electric field for those, charge distributions, right? And that's what we do. I can use, I can start with the Gauss's law, find expression for electric field, and then plug in into this equation for the potential, then use that to solve the potential. Or as we saw before, right? We can go other way around, right? So find the potential in a different way, and then use that to find the electric field. So obviously, it depends completely on the type of problem we have. What is it asking? But those are our main equations. So let's say we have potential, which we can find from this ratio of potential energy per unit test charge, or from this integral. Okay, where a lot of times the electric field we can find using the Gauss's law. All right. So again, in terms of, these are several slides where it allows you to sort of like have a strategy on how to approach a problem like this. First, when you're given a problem, conceptualize. Think carefully about the individual charges or the charge distribution you have in the problem. That means, are you given a system of particles? Let's say two, three, four, five, particles, point charges, for example, and want to find the potential due to those finite number of particles. If not, if yes, then that's a straightforward problem. You just find potential due to each charge and just add them together algebraically. If you have a continuous charge distribution, then you have to do the integral. Again, it's a little bit simpler integral, but still, it's an integral nevertheless. You have to, approach it the way we did for the, electric field due to a continuous charge distribution. That means use the symmetry, maybe even use a Gauss's law to get the electric field, and then use the integral to find, let's say, the potential. Okay. Again, so categorize, are you analyzing a group of individual charges or a continuous charge? And the answer in this, will let you know how to proceed in the analyze step, which will be then the next one. All right, so when working problems involving electric potential, remember it is a scalar quantity. So there are no components to consider, which is, makes, at least, the expression, right, much simpler. Because before, if we are doing, for example, x component, and it was like the integral of k dq over r square, then if it's x component, then we probably would have had cosine of theta or sine of theta, where in this case there is no such thing, as for potential, there is no such thing as component. So it's always going to be just dq, so k dq over r. That's it. There's no sine or cosine, additionally added to that, which sometimes make our calculation or integrals a little more complicated, because a lot of times this guy here makes our calculation a little bit difficult, where we had to do the trip substitutions and things like that. Anyways, so using the symmetry, try to then find potential due to the, let's say, either system of particles or a continuous distribution. Right, so with the potential energy in mechanics, only changes in electric potential are significant. So that's kind of like the important thing also when you're dealing with the potential. You only care about those 2 points, point one, point two, or point A, point B, right? That means, everything else is pretty much, arbitrary. Okay. So when dealing with the point charger or a finite size charge distribution, we usually define v equals 0 to be at the point infinitely far away. Again, because when we're doing the change in potential or change in potential energy, it's always simpler when the other point is infinitely far away and it's 0. All right. So this is kind of like, let's say, if you are analyzing a group of individual charges. So let's say you have 1, 2, 3, 4. This is your Q1, Q2, Q3, Q4. Those are source charges. And you want to find the potential at point P. All you have to do is find the potential 1 due to charge 1. Then find the potential 2 due to charge 2. Then potential 3, then potential 4, and just add them together algebraically. That's it. Relatively straightforward. So it's just the algebraic sum of those individual potentials. Some could be positive, some could be negative. That depends on the source charge. But remember, to find the net potential at that point, you only need source charge and the distance. That means to calculate V1, you say K Q1 over R1, and this being the R1. And then the same thing for all of them. If you're analyzing in continuous charge distribution, replace the sums for evaluating the total potential basically with the integral. Okay, that means you're going to integrate, from point B to point A or something like that, right? So from A to B or B to A, depending what are those 2 points. So the charge distribution is divided into infinitesimal elements of charge dq located at the distance r from point P. Okay. So an element is then treated as a point charge. Okay. So the potential at P due to the element here is given with dV equals K. This E here is a subscript. So it's basically KE dq over R. So this is then dV. Okay. Remember, this is just from a single element, how it contributes to that point P. And then obviously what we do here is we then take the integral and basically integrate from between, like, let's say 2 points of interest. All right. Then to obtain the potential from the electric field, we then can say, all right, change in potential equals the, negative of the integral of that, right? E dot ds. And as I mentioned, right, so this is basically can be a series of, integrals that we would have to do, where this electric field independently can be calculated from the electric flux, where E dot dA can then be used, where it's equals to Q enclosed over epsilon naught, right? So then we find electric field from this and then plug in back and calculate the potential. All right, so finalize, check to see if your expression for the potential is consistent with the mental representation and reflects any symmetry you noted previously. Because you also want to make sure, right, that, is the value correct or not. That means, for example, if you have a distribution that is, let's say, overall is a positive Q, and you're calculating the V here, well, if you get a negative number, right, -5, let's say, volts, it's not, it doesn't make sense, because this is a positive distribution. You cannot get a negative number over there, right? So that means you want to also look at it in terms of, does it make sense or not? Is your calculation correct or not? All right. Let's look at that in an example here. Previously, we had a exactly same problem where we had a ring where we have a uniformly, basically the charges are uniformly distributed. So it's a uniformly charged ring. And previously, the question was to find the electric field at that point P due to this, configuration. This time, we're going to find electric potential due to this configuration. Because, if you have the same, if the ring, which is charged, this ring, which is acting like a charged source, right, gives us two things that we can calculate at point P. We can calculate potential and electric field, right? I already showed you how to calculate electric field for this configuration. Now what I'm going to show you how to calculate potential, and then even how to calculate electric field, not using the, let's say Coulomb's law, but how to find the electric field using the potential. Okay. All right. So let's look at then what we have. It's a uniformly charged ring. So that means, in terms of, like, let's say those steps, right? When you are looking in terms of, let's say, categorizing what type of problem it is. Well, this is not a system of charges, right? But it's a continuous charge distribution. That means I choose a small element and I say that dv is equals to then k dq over r. That means at this point p, the contribution from this dq is given as k dq over r. All right. So then what I need to do here, I need to then integrate both sides, where the left side then becomes v equals, um, well, technically it's delta v, but I'm going to take the other point to be infinitely far away. So let's say v is equal to an integral of k dq over r, and r is going to be then x squared plus a squared, because this r here, right, can be written as square root of a squared plus x squared. Because it's just r, not r squared, I have to include the square root. All right, so this is basically my equation. Now, there are several ways we can technically solve this problem. I can look at it in terms of, all right, so if I go around this ring, by the way, also notice that there is no sine or cosine, because we don't need that, right? There is no component to this potential. It's just a number. This is all we need. So think like this. As I go around this ring, the question here is another dq, another dq, another dq. If I choose different dqs, will that give me a difference in terms of this expression? Let's say, will there be a different distance r for, let's say, dq2 or dq3 or dq4, right? Are they going to have a different, expression? Because the idea here is this. Remember, dq is equals to lambda dl, right? Just like I said. That means if I take the size of this, right, size of this to be dl, so then I can say that this is dq equals lambda dl, and dl is its small element, arc length element. Okay. Because one thing I can do here is this. I can replace dq with lambda dl. That means, sort of like, let's say, I can use this equation, which is, let's say, version 1. And the reason I can use this equation, because by what I mean by leaving dq there, because any of those elements, dq, dq1, dq2, dq3, 4, right, they exactly have the same distance r. That means everything is basically constant. That means the equation just simplify to this: k x squared plus a squared, right? I can remove that because x is the same for all of them, a is the same for all of them, and just integral of dq going from basically from 0 to q, which then if I integrate, integral of dq just becomes k q over x squared plus a squared. Okay, so that's it. This is what I get. But then I can also do it in terms of, let's say, version 2 of this equation, where v is equal to an integral k, but then I'm going to replace dq with lambda dl over x squared plus a squared. Now, what I'm doing here is I'm going to then replace dq with dl. That means I'm saying that this is a small element, but then I'm going to, when I'm integrating, go around the, the arc length of that, ring. That means I'm going to go basically from 0 to 2 pi r. All right, so it's actually a here, right? So 2 pi a, right? So going around a circle, 2 pi times the radius, and the radius is a. So I can use this. So basically becomes k lambda divided by x squared plus a squared, and then becomes integral of dl going from 0 to 2 pi a. Again, what is 2 pi a? Is circumference, right? So 2 pi a. Now what I get here is I have then k lambda over x squared plus a squared, and then in this integral just gives me 2 pi a. All right, so, well, it doesn't look like this equation over here, but remember, so what I have here is technically then lambda is equals to q over l, where l here is the entire arc length. So technically I can replace this with, oh, I have it here. So it's 2 pi I, right? So lambda is q over 2 pi a. That means if I replace this q over 2 pi a, those cancel out, and I end up with the same equation as this version 2. Right, so there's also version 3. Technically, we can do it another way. So this is v is equals to an integral of k. I'm still using, I'm replacing dq with the lambda dl. But in this case, remember, the in a way, L here is the arc length. And remember, it's equals to then the radius A, then times, angle theta. Uh, so let's say I can, call this, as I move like this, right? Let's call this some theta, angle theta like that. Or let's call this phi, I guess. So angle phi. So A times phi. That's basically my arc length equals A times phi. Well, then that means then dl is equals to A times some d phi. Okay, where that means, it's lambda times dl, and dl is then A times d phi. That means k lambda A d phi then equals x squared plus a squared. Now, I am going to be then using this change in angle phi, right? So if I start from here, then my angle changes. What changes going from 0 to 2 pi. Now, removing all the constants, k lambda a over x squared plus a squared, then integral of how the angle changes, right? D phi going from 0 to 2 pi. Well, you can see, right? So this integral gives me nothing but, let's say, 2 pi. That means what I end up with here is k lambda a, then 2 pi over x squared plus a squared. Again, then what do we do with this? Well, again, remember that q here is equals to, lambda equals q over L, or q over 2 pi a. So if I replace lambda with q over 2 pi a, the a's cancel out, 2 pi's cancel out, back to exactly the same thing. So that's why what we have here is probably the version 1 is the simplest one, assuming because they have all those dq's, right, have exactly same distance r from a point of interest because of the symmetry, then we can just use this version over here. Okay, sometimes this doesn't work. That's why I'm giving you like 3 different ways. Technically, you could have evaluated this integral. All right, so that's, basically is part A, finding the potential due to this distribution. Okay. Part B, it says then find the expression for the magnitude of the electric field at that point P. All right, that means, if I want to find then the potential electric field from the, using the Coulomb's law, we could have done that. I showed you in the previous, videos. But what I'm going to do here is this. Since we have the potential, which is kq over x squared plus a squared, using the symmetry, we can see, right? So let's say if this is my ring at that point P, what I have here is, get that? So what I have here, this is being the R, right? So I already have the electric field, and electric field, if you recall the previous example, is going to be something like that for this, dq, or something like this for the other dq over here. And if I'm looking at then this components in this direction, they all cancel out. And only the components that are basically along the x-axis add up to one another as vectors. So then technically all I have to do is just look at the EX, or horizontal component of the electric field. All right. So using this, I'm going to say, all right, so EX is equals to, remember, right? So we can find the electric field from the potential, because EX is equals to negative partial derivative of V with respect to X in this case. Okay. So since everything is 0 right now except the X component, so I can just say it's just basically dV dx. That means taking this equation and just taking the derivative with respect to X. Then EX is equals to negative derivative of KQ over, let me write it like this, probably simpler to write like that, right? So KQ, then X squared plus A squared 3/2, right? So then taking the derivative of, this guy. And what we can see here is, kind of very similar to the previous example that I did. So then EX is equals to negative. So KQ can come out because they're constants. And if I'm doing taking the derivative of that, so that becomes, all right, so I made a typo here. So this is 1/2, sorry, negative 1/2. Okay, so it becomes negative 1/2, then x squared plus a squared then becomes negative 3/2. And then I also have to do the, so like let's say what I have inside the argument, right? Taking the root of x squared, so it gives us 2x. Okay, then x component is equals to, so what do I end up with? This 2 cancels out, and then this negatives cancel out. I have then k q x over x squared plus a squared 3/2. And that's my answer. So k q x over x squared plus a squared 3/2. That means you can say, right, once I have the potential, which is much simpler to calculate than the electric field, for a distribution like this, all I have to do is just take a derivative of this with respect to, like, let's say, specific component of the E that I'm calculating, and find the electric field using this approach, which in my opinion is much simpler than what we did in the previous chapters. All right, always finding the potential first and then electric field is generally simpler than electric field directly. Let's look at here another example. A rod of length, should be length L, sorry, located along the x-axis and has a total charge Q and a uniform linear charge density lambda. We want to find the electric potential at the point P located on the y-axis at distance a from the origin. All right. So for this one, then what I need to do, again, first thing, try to understand, conceptualize, right? Visualize what type of problem we're dealing with. Categorize this to be continuous distribution. And then understand that what we need to do here is choose a small element. And this small element has a size dx and charge dq. Find its position relative to the point P, and then relative to, let's say, some reference position. And this, like, let's say here 0, right? Or like, let's say one end of the rod. Then I can say that potential dV of this particular element is equals to integral of k dq over r. Okay, so k dq over r. All right. Then obviously, oh, sorry. It's technically, when I'm doing this, is k dq over r, and then I'm taking the integral of both sides. So then v is equals to integral of k dq over r. All right. Now, what I can see from here is that r is equals to square root of x squared plus a squared. So then I can replace it with that, right? K technically can come out. That's the one constant that always can come out. Then I have dq over x squared plus a squared. All right. So then from here, what I have here is I cannot just integrate in terms of dq, simply because this x squared plus a squared is not a constant anymore. Because if I look at this small element over here, let's say I chose this element, let's call this dq prime. See, its distance from the origin is x prime. If I chose different dq, let's say double prime, its distance is x double prime, and those x is not equals to x prime is not equals to x double prime. That means x is not constant. It cannot come out. Okay, so that means it's part of my integration. Then what we do here is we say, okay, then dq is equals to lambda dx. That means, remember, right? Lambda is equals to total charge over total length, or is equals to then dq over dx. That means the ratio of the total charge over total length, or element charge over element length. Okay. Then rearranging, dq equals lambda dx. That means here I can say that this is k lambda integral of dx, where this is x squared plus a squared. Basically, what I'm doing here is I am replacing dq integral from dq integral to a dx integral. And this is simpler for me because then I can integrate this, simply going from one end, which is 0, to another end, which is L. So going from 0 to L, it's just a line integral. Okay. All right. So then from here, what we can do is we can say, all right, so then it's K times lambda, and this integral. All right, so this is not a straightforward integral. So I'm going to just go ahead and give you the answer. But the idea is that for this type of integral, there requires a couple of substitutions. For first, we can say u equals x over a, which then gives us du dx equals 1 over a, du equals, um, or a du equals dx. So then make a substitution where, we're substituting, basically x as, or x squared equals a squared u squared. So taking this, substituting for x, taking that, substituting for dx, and getting the equation, which we end up with in terms of du. So becomes 1 over square root of u squared plus 1. And then from that, we do a trig substitution, where then u is substituted with the tangent of some other constant. So anyway, so I imagine if you really want to, you should be able to do that, but you can also refer to like one of those integral tables and be able to, find that equation. This equation will give you in terms of ln x plus square root of a squared plus x squared. And let's say going from 0 to L. And then we can calculate and replace lambda with q over L. So it becomes k q over L ln L plus square root of a squared plus L squared minus ln of a, which then can give us k q over L, then ln of L plus square root of a plus L squared over a. And that will be our answer. You can see, right? No matter if you're using technically a potential, it is still relatively difficult to work with the continuous distribution problems. All right, so then what we have here is how to find electric potential due to a charged conductor. Okay, so this is not a point particle, not charge distribution, more like some kind of metal conductor that, if you remember, we looked at a conductor like this to have all the charges on the surface of a conductor. And when we use the Gauss's law, let's say for some kind of any region inside the conductor, we would get electric field equals 0, because conductors push all of those extra charges to the surface and there is no electric field inside the conductor. Now, if you are then applying this equation for that, when we're saying that let's choose 2 points, right? Some point A, then point B, then changing potential between point A and B, VB minus VA equals integral, right? So what we're going to do here, we're going to say E dot ds equals 0. That means electric field is always perpendicular to displacement, and E dot ds equals 0. The potential difference between points A and B also 0. What it means that VB is equals to VA, which means same potential everywhere on the surface. Same thing we can also do, on the surface, or even we can do like in terms of inside the conductor. So we can see, right? But potential is constant everywhere on the surface of charged conductor in equilibrium. And delta V equals 0 between any 2 points on the surface. Remember, delta V being 0 means that those 2 points that we're considering have exactly the same potential. The surface of any charged conductor in electrostatic equilibrium is an equipotential surface. Remember, what the equipotential surface means, that any surface that you're considering have exactly the same potential. Now, because the electric field is 0 inside the conductor, the electric potential is constant everywhere inside the conductor, which means that if I go back here and I'm choosing that, for example, point A to be not on the surface, but somewhere over here, this is my point A, then if I'm considering point A and point B, the right side of the equation, which is this integral, is still going to give me 0. It's going to give me 0. which means then again, VA will be equals to VB. That means same potential here and everywhere inside the conductor. All right, so if I do that, that means potential at, let's say point B, which is the surface, and any point inside point A, including the center, right? If my point A is exactly the center of the conductor, my potential will be exactly the same. Because if I'm doing VB minus VA equals negative integral of E dot ds going from, A to B, right? Well, it considers, let's say integral and, inside the conductor all the way from point A to point B, and this is zero. Well, if this is zero, it means VB minus VA is constant. So VB minus VA is zero, or V is constant. So VB equals VA. So that's why if I'm looking at the kind of like a diagram like this, what I will see here is potential not zero and constant everywhere inside the metal conductor, from zero, R equals zero, to all the way to R equals to the radius. And then after that, it dropped as K, KQ over R. For the electric field everywhere inside the conductor is zero all the way to the radius. And then at the surface, after the surface, it drops as 1 over R square. Okay, those are the main differences between a conductor, or the potential for the conductor, or the electric field for the conductor. Okay, now we'll have here a non-spherical conductor. So you can see, right, the surface charge density is high when the radius of curvature is small. That means, for example, if I break it down into smaller, sort of like a curvatures like this, right? Say this is a smaller radius, this is a larger radius, which means that electric field magnitude will be larger. Okay, so the electric field is large near the convex point, having a smaller radii curvature. That means electric field magnitude will be stronger here, and strong, and weaker in these regions. All right, so we can also have a conductor with some kind of, a cavity. Okay, so suppose we have a conductor of arbitrary shape that contains a cavity. Okay, so let's assume no charges are inside the cavity. Okay, in this case, the electric field inside the cavity must be zero, regardless of the charge distribution on the outside surface of the conductor. Okay, the field in the cavity is zero, even if an electric field exists outside the conductor. Okay, that means regardless what you have here, there's a zero. But you can also have a cavity there, and there's a charge over there. Then what we get here, let's say, if then the charges will be distributed such that, let's say this is negative, let's say this is positive. Then depending what type of charge we have inside, that we can have then accumulation of charges again here inside that second surface. So you get two surfaces, outer surface and inner surface, and there's a charged particle inside this cavity. Then you also have a charges distributed on that inner, surface. Okay, so every point on the conductor is at the same electric potential. Any 2 points on the cavity's surface must be at the same potential. So imagine an electric field exists in the cavity, right? Evaluate the potential difference with VB minus VA equals negative of integral between AB E dot ds. So this is basically, if you're looking at this, right? So if those are the 2 points of interest, A and B, then what we get here is, if you're integrating, the integral must be zero, since delta V equals zero, because potential difference exactly the same for point A and point B, because it's the same surface. That means we can conclude that there is no electric field inside. Okay, only true if the field is zero everywhere in the cavity. All right.